Diarmuid Crowley, speaking on relative kappa-classes.
Thank you, Michael, and I'd like to thank the organisers for the chance to speak and indeed to give the last talk of the conference. It's been a very stimulating week, I hope you'll all agree, so I also have the pleasure of thanking the organisers. I think it's fantastic to see the energy, the new ideas, the interactions between homotopy theory and manifold theory, so thank you very much to the organisers. Yeah, I want to report on new work with Thomas Schick and Wolfgang Steimle, very much inspired by work of Michael Weiss, so I'm very happy that Michael's here. We're going to be looking at D manifolds. D is going to be very big in general, and the space we'll be interested in looking at is the diffeomorphisms of the disk. Everything will be relative to the boundary. So we take some disk in the interior of our manifold, and we have seen that this space has very interesting topology going back to Wolfgang. Everything is also going to be rational in this talk. And we have the extension map, and once you find some interesting topology here, it's a very natural question to wonder, does it survive here? Okay. So we take a diffeomorphism, it's supported in the disk, we extend it to some random manifold. Could the topology of that manifold somehow untie the topology you see that's present in the disk? Okay. Now, it turns out that it's a good idea to think of this by comparing it to the homeomorphisms of the manifold. I'll denote that by top to save a little bit of time. Now, by the Alexander trick, this space here is contractible. So as is often the case in topology, this is a hard problem, but often relative problems can be easier. So what we see is a relative problem. So we get a map of pairs. And we also know that this evaluation map, of course, it's a homomorphism, so it induces maps of classifying spaces. So maybe let's look at the corresponding pairs, okay? So this is in some sense the central diagram of the talk. Okay. So if you have a homotopy class here, you know, this group here is isomorphic with a shift to a homotopy class here. So let me just in one sort of line give you the slogan of the talk. We're going to construct some families here. The Weiss stands for the W stands for Weiss, excuse me, and these will belong in 4i minus D homotopy of this space, rationalized. And the title of the talk, Relative Kappa-classes. This is perhaps an obvious notion. If you take a surreal Pontrjagin class as discovered by Michael, it generates a kappa-class that's in cohomology of the above space. And the talk is, the main result of this talk is that these things pair non-trivially. So that's going to give you these Weiss families correspond to interesting rational homotopy groups here, at least relatively. They're detected in the cohomology, and so you know they're still non-trivial in the relative group, and now you get to try and have fun of figuring out whether they are coming from diff dn or top dn. Okay. So that's the general story. This seems to be at least it's not really new. It's a kappa-classes is a very simple idea, but I'm not clear that people have written down relative kappa-classes before, so this is maybe technically new and helpful. So these are the relative kappa-classes. So there's a theorem of Weiss, And I'm not going to worry about the particular range of dimensions, but there exist pairs of integers I and d, such that if you go to the fourth ith cohomology of B top D, everything's rational. We have the ith Pontrjagin class. It vanishes, so in BOD, okay? So there's a certain range. If you take a vector bundle and D is small enough, the ith Pontrjagin class will vanish. Somewhat surprisingly, perhaps very surprisingly, that's not true for a topological bundle. So you can have small degree bundles that have Pontrjagin classes non-zero when they oughtn't to. And in terms of the notation, that means they come back to the relative group. Okay? And in fact, this map is injective rationally, so there's a unique lift. And for today's talk, this is what I mean by a surreal Pontrjagin class. And if you want to know more about the ranges for which such I and D exist, there's Oscar Randal-Williams has work on this telling you about the smallest I and D, at least for D even. Okay. So in any case, Michael produces for us these surreal Pontrjagin classes. He does a little bit more. He also tells us that they evaluate non-trivial in homotopy. So moreover, there exists homotopy classes. What's my convention? I'm putting so the A, the I is non-zero in Q. Okay. So these surreal Pontrjagin classes evaluate non-trivial in homotopy. And you can check by the similar reasoning that these homotopy classes can't possibly come from BOD or mapped. So these classes remain non-trivial here. In fact, of course, they're so I'm going to adopt the convention of using bar for relative things, right? All right, so far so good. Here we're just looking at the linearization. Now I want to describe how smoothing theory will give us this class here where we add the W. So in general, smoothing theory will tell you about how to compare the space top D mod diff D. And in particular, if you apply the theory to top DD mod diff DD, you get that this is homotopy equivalent to the D plus one fold loop space on top D mod OD. That's often called the Morley homotopy equivalence. And if you think a little bit more about this, let's see. I want to use this. Have one less loop. Loop D of this pair. D top D, D OD. Right. So that's going to contain. This group is isomorphic to this group here. So we have our A bar, and we will get the Morley isomorphism back to the 4ith. I might give myself a bit more room. Yeah. So there's an isomorphism here, and we'll call this a Weiss family for any class coming from here on which the surreal Pontrjagin class is non-trivial. And if we go by the boundary map, remember that this is an isomorphism since this space is contractible, we get a family of DD bundles. So let's call that AW here. So that's the notation.
It's not omega D?
Sorry?
The omega D plus 1 should be a D.
No, this is correct.
On the left. Or the homotopy group index.
Oh, yeah. Oh no, I think this is right. This is right.
Oh yeah.
But I think the first thing that you pointed out is not right.
This one here?
Like BDiff.
Oh yeah, this one's not right. Sorry.
I was right. So one loop. No, leave it.
Well, I'll write it that way.
All right.
Okay.
Thanks. Sorry. Okay. So that's remember the key point of the talk is to show that we have this non-trivial pairing. So here's this homotopy class, these families, and now I have to tell you about what a relative kappa class is. Okay. Now the idea of let's say absolute classes is familiar. You take a family of manifolds, it's got a vertical tangent bundle, you take some classical characteristic class of the vertical tangent bundle and fiber-wise integrate it. Okay, so now what's our setup going to be? What would it, so here's a schematic picture, here's some space X, it's a pair X comma A. So, and then here's just a picture of a bundle, E. So E is going to be a bundle over A. So E to X is a topological, so it's a top M bundle. And we're going to smooth it over A. So over A here, we've got a smooth structure on our bundle, okay, and is going to be trivialized on boundary M, okay, in the case that M has a boundary. So we just want to consider bundles over any space, any pair X comma A. It's a topological bundle. When we restrict to A, we give it a smooth structure, okay. So coming out of here, in the first place, we have a vertical tangent bundle, that vertical tangent microbundle, if we want to be precise, that's going to be top D, okay? But on some parts of this diagram, the vertical tangent bundle is smooth. It's coming from a smooth family, okay? So since it's a smooth manifold on, we'll call this the fiber-wise boundary, we have a smooth structure. And then on E restricted to A, we also have a linear structure on our vertical tangent bundle. So in this picture, all of the boundary of E is mapping into BOD. Okay? So in the general theory, if I take, in this class, in this talk, we'll only apply them to these surreal Pontrjagin classes, but in general, if you had such a relative cohomology class, you would take the vertical tangent bundle considered as a map, you would pull it back, and this would live in the cohomology of E relative to its boundary. And you, in this such a setting, you can still fiber-wise integrate. So you fiber-wise integrate down here, and this is what we mean by the relative kappa class. Okay, so there's nothing terribly surprising about this construction if you think about kappa classes.
So it's not just relative to the boundary of E, it's also relative to the image of A?
Yeah, so over A we've got a diff structure. So here the vertical tangent bundle is mapping into BOD. Right, and along the fiber-wise boundary it's trivial. So here we just see the tangent bundle of the fiber, and it's smooth.
What bit are you calling boundary of E?
Well, E is a manifold. Oh, sorry, excuse me, yeah. Let's suppose X was a manifold with boundary, then this is literally the boundary of the...
Those two.
Yeah, so it's a... Yeah. Thanks. Okay. So, in any case, I don't know if people have previously defined relative kappa classes. If you think to define relative kappa classes, I think this is what you would do. It's a very natural notion. And it will be of some use for us. So I'll just write down some basic properties once you have this definition of relative kappa classes. So if the boundary of M is non-empty and E is trivial, so I mean it's the trivial family just everywhere, then kappa C is 0. There's a gluing formula, so suppose I had two of these families and I glue them along some component of the boundary, okay? So they're trivial along the boundary, so I can glue them along the boundary, all right? And then now I take my relative kappa class of such a gluing, right? So this is along the fiber-wise boundary. Glue along the fiber-wise boundary. Then you have a nice sum formula. The kappa classes also behave in the way that you would expect them to. Okay, so I have my class C, it's a relative class, I could forget that it's relative and map it over to B top D, okay? I think of kappa as giving some map to the cohomology of B top. So this square commutes. So if we call both these maps J, what we're saying is that if I take J of kappa C, that's kappa of JC. Okay. And I'm going to run out of room. So the fourth property will be a key property for this talk, and that's a version of naturality for extension. In fact, it follows from the additivity property.
So, this, in your third diagram, on the right-hand side, are there some minus D's?
Yeah, of course, thanks.
And then the bottom left corner, or something else? But I really want to ask him, one, why do you need a boundary to be non-empty?
Sorry?
Why in one do you need a boundary to be non-empty?
I guess in some sort of totally degenerate case, you could have a manifold where the kappa class restricted to the fiber was just non-zero. Well, you see, if you've got a pair, you've got a relative cohomology class, and since it's since you have the map be M comma boundary, am I right over here?
Just say if A is not empty, for example.
Yeah.
If A is empty.
Yeah, I mean, I'm just being careful here. Maybe you can do better than me. That's fine. But that's all I want it for. So let's remember that we have extension gives us a map of pairs. So we were interested in the cohomology of the top BD, BDiff, BD, and there's a map here, B top M to B diff M. Okay, so that's a homomorphism, or sorry, that's a map of pairs, and we have defined a kappa class here, and it maps to the kappa class here, hence the notation. So it's a little bit confusing at the moment, so let's imagine in general we decorated our kappa classes where the manifold. Okay, so these are the basic, once you've defined relative kappa classes and you think about what their basic properties should be, it's pretty easy to prove these lemmas. So one nice thing about these surreal Pontrjagin classes It's determining when the kappa classes are non-trivial in the closed setting is of course very challenging in general, but not so for the relative kappa classes of surreal Pontrjagin classes. So for all m, right, let's take the evaluation map applied to this Weiss class and evaluate it on kappa pi. This is non-zero, okay? Okay. So, yeah. And this should have a hat on it, right? So this is in the relative cohomology of top rel diff. This is in the relative homotopy or homology. We push them forward. And okay, I'll give you a one-line proof in a second. But let's look at some obvious consequences. So in the range that we have surreal Pontrjagin classes, of course the corresponding groups are non-trivial, right? And if these classes are non-trivial. So there's a non-trivial element here which is detected by the relative kappa class. Right? In particular, the statement is this kappa class is not zero here, and the Weiss family is not zero here. Okay.
What do you mean non-trivial? Because when I is very big.
Well, only in a range. I'm just saying if I have such a class,
Okay.
right, and then this statement holds. Of course, maybe the notation is not great, but of course the indexing here is this class was constructed from these PIs, right? So if you have a surreal Pontrjagin class, you'll have a corresponding Weiss family, and those two families, that corresponding kappa class pairs non-trivially with the corresponding Weiss family. Okay. And I leave it to others to figure out. To me, it's a miracle such things even exist. I leave it to others to figure that out. But if they are there, then this relation holds between them.
So is the only thing you've used so far that these Pontrjagin classes pair with something that comes from a sphere?
Yeah, I mean, well, let me say something about the proof. By naturality, okay, we reduce to doing this on the disk, right? Okay, sorry. The thing that we're interested in happening in a general manifold, so here, so by our formal property that's, all right, we're just doing this, M. Now we've said that this is this, so this is the kappa class of the surreal Pontrjagin class on the D disk, okay? So now we simply have to verify this is non-zero, and this is tautological, so this is non-zero, that's tautological via smoothing theory. I mean, we built these classes such that this statement is true. Okay. We can make a little definition on the disk. If you have relative classes, I think more generally one might wonder what secondary classes are, but this is an element in 4i minus d minus 1 of the cohomology of BDiff dd. Okay. And that's by definition the thing that maps to. That's just a definition, and this is non-zero. Okay, the groups are isomorphic. Right. Yeah, so this seems like a reasonable class. It's a secondary class. You have it because the kappa classes vanish here, and that's because this space is contractible. Let's do an example, and I'm grateful to Oscar for pointing this example out. So let's take M to be a WG, and let's consider corresponding long exact sequence. So here we are in B top WG relative to B diff WG, and we have our non-vanishing relative kappa class. We might wonder which way it goes in our long exact sequence. Okay. And this, when I did this exercise, this was a nice reality check because it really goes back to Michael's proof of the existence of the surreal Pontrjagin classes. So that's not a D anymore, this is a WG. Yeah, good. So thanks to the work of Galatius and Randal-Williams, once G becomes large, this group here is 0, okay? So this injects, and we've already said that this maps to that kappa class, right? So we conclude that this kappa class is non-zero, and well, that's how Michael proved the existence. It's one point of view on how he proved the existence of the surreal Pontrjagin classes. He produced a WG bundle whose vertical tangent bundle had a non-trivial Pontrjagin class when it shouldn't have. So that's nice to see. At least these computations are consistent. Okay. Now this brings us to our second main theorem. So far we just talked about cohomology, but what about homotopy? These Weiss families live in homotopy groups. So, you know, just because the corresponding cohomology class dies doesn't mean that your family will necessarily die in homotopy. And the nice thing about having relative kappa classes is that in certain situations you can analyze this question. So let me just tell you what am I thinking about. We have now identified a class in 4I minus D for any manifold B top M relative to B diff M. Alright, that's the evaluation on a Weiss class. And there's of course a boundary map for the 4I minus the minus 1 of B diff M. Okay, so that's the initial question we came back to. We have some interesting homotopy class in the diffeomorphisms of a disk, and we're trying to see if it lives here. Okay. And theorem B says that this map is non-zero if the total Pontrjagin class of M is 1, right? So it's trivial. Then this is the boundary map. Okay. So in particular, the WDs are stably parallelizable. So in particular, WGs. So we have a situation where we found something in the kernel of Hurevich for a WG, right? Because corresponding homology group is trivial, but on homotopy our class is non-trivial. Okay. So A bar W kernel. Well, I think this is true. Well, unless I'm making some mistake with finite generation. Certainly if these things had finite type, which they probably do in this range, that's okay. I don't think this is right. Okay. Okay, so
Sorry, PM is the total Pontrjagin class? Or?
yeah, total Pontrjagin class. Yeah, sorry. Yeah. And this is rational, right? Everything's rational. So it's just saying that if the so the proof of this statement is a nice diagram chase. So I can give the proof. Or at least an outline of the proof. So step 0, assume M is closed by doubling with the identity. Okay, so we're trying to show that something's non-trivial in homotopy. So what am I saying here? We have another extension homomorphism. We're in homotopy of BDiff of M. Now I'll put the boundary in, and then I just extend by the identity, right? So it suffices to show that it's non-trivial here. BDiff of M union M with the identity. Okay. So if it's non-trivial in homotopy here, it's non-trivial in homotopy here. So without loss of generality, if you like, I assume I have a closed manifold. So what's the diagram I'm trying to think about? I have a class here in this relative homotopy group, this Weiss class. Okay, it's non-zero here, right? So here's E star of AW, right? And it's detected by this relative kappa class, right? So that's a map to Q. And I want to know that it's zero, its image is zero down here, right? Right. So, one way to think about this is when the Alexander isotopy, I mean, there's only one way to trivialize these families over disks, but now with the topological manifold, we have to think about all the possible ways that we could trivialize a given smooth family, okay? So, B top M, okay? So, this is an exact sequence, and here we have the kappa class of Pi. This diagram commutes, okay? So we're looking at, if we have some class here, which is the boundary, we just look at the different ways. So it suffices to show that this is zero. If this thing is zero, then every possible lift will have the same value here, okay? So it suffices to show kappa Pi equals 0 on this homotopy group. Right. And this you can do by analyzing, well, what's a homotopy group of a BDiff? That's a family over the sphere. And this is a trick that Wolfgang, Steimle, and presumably others used with Hunker and Schick to analyze the kappa classes of such families. Okay. So what do we have? So given some class X in our homotopy group, B top M, right, we form E of X. So that's the corresponding family, right? Which is a bundle over the 4ID, right, with fiber M, okay? Now M is closed, right? Now, because of the way the dimensions work out, in fact, now we have our map here, our vertical tangent bundle into B top of M, right? Now the base space is stably parallelizable, and we're trying to analyze a Pontrjagin class, right? We are interested in determining the ith Pontrjagin class of the vertical tangent bundle, right? Sorry?
Target of the vertical tangent bundle?
Oh, yeah, thank you. Great. Yep. So we're trying to analyze this, but this is in fact the same thing as the Pontrjagin class of the total space, okay? Because the base space is stably parallelizable, right? So the tangent space here is the sum of the vertical tangent bundle and the pullback of the tangent bundle of the base. Now here's a little trick. Now we know that since we have a bundle over a sphere, the signature of Ex is equal to 0. But that's equal to Pi of Ex, since the decomposable Pontrjagin numbers vanish. I mean, I guess I'm assuming that 4I minus D is bigger than 1. Right? So if you have a bundle over a sphere, the decomposable Pontrjagin numbers will vanish. Since the fiber here, let's use our argument. We just look at our spectral sequence, right? A Thier-Herzebruch spectral sequence. It's got 2 rows, and we're assuming that the fiber is stably parallelizable. So if I take some other random Pontrjagin class of Ej, it's 0 when I restrict it to the fiber. So it has to come from here, and when I take it square, there's nothing left out here. Okay. All right. So Weiss families on homotopy survive into the homotopy of any, in particular, stably parallelizable manifold. So that's a nice thing about taking this relative point of view. You show that you have this thing that's non-trivial in the relative group, and now you can try and figure out which way it goes. Does it go into diff, or does it come back from top? And under certain circumstances, you can show that it goes into diff. Okay. Now, for that theorem, we used a statement about the vanishing of the kappa classes in top bundles, but only for bundles over spheres, okay? If we want to show that this Weiss family survives in homology of BDiff, we can repeat the reasoning so long as we have a stronger input, so long as someone told us every kappa class here was vanishing on homology. Right, so just take this diagram here, replace homotopy with homology. I'm trying to show I have something non-zero here in homology. I'm trying to show that it goes non-zero there. I have a homomorphism detecting it. I look at all the possible ways I can vary it. If the kappa class vanishes on all the possible ways I can vary it, it goes non-zero here. So it's the same diagram chase, but we need stronger input. We need someone to tell us for a certain manifold that the kappa classes just vanish, period. And thanks to Hebestreit, Lueck and Randal-Williams, you can make such a statement for a large class of aspherical manifolds. So that's theorem C. So theorem C. Let M be closed aspherical. Now, in principle, I should put some condition on D, aspherical, smooth, all manifolds are smooth, but probably D bigger or equal to 5, but that will be guaranteed on the assumptions we had to make to get the surreal Pontrjagin classes in the first place. These typically have to be very large. And there are extra hypotheses which I don't want to get into, satisfying a version of the Borel conjecture. So I'll just write this in plus a conjecture by Bergalia, plus conjecture Bergalia. But in particular, if you like, you can take M to be the D torus, and that will satisfy the assumptions. So then, Right, boundary E star of the Weiss family is non-zero, but now in the homology of BDiff of your aspherical manifold. Okay. Right, so it's important to know these. And the proof is you invoke Hebestreit, Lueck, Randal-Williams, and chase with homology as before, instead of homotopy.
So in that theorem, we only proved that they vanish on the identity component of BDiff.
Oh.
I guess that's almost we proved it for the whole thing, but maybe in general only for the identity.
Oh, okay.
Yes. But if you put a 0 in diff, then it's true.
Ah, yeah, thanks. Good point. Good. Yeah, thanks. Okay, so they are the main theorems which I wanted to state. So that's so far what we've been able to do with these relative kappa-classes. Thanks to the work of Weiss, we actually had something to work with. Once you have the definition, you verify some basic properties. You end up with non-trivial elements in relative homotopy and relative homology, and then you get to work trying to figure out where they go. And sometimes you can say something. So I know this is the last talk of the conference, and I will just run for a few more minutes. I just want to make two remarks. So actually, one of the motivations for thinking about this was, at least up until Michael's work, as far as I'm aware, we didn't have rational homotopy on even-dimensional disks, diff of even-dimensional disks. Maybe other people knew better, but I certainly didn't. So I want to mention a construction of Evans and Rizal. Which motivated the problem. They have a map in symplectic topology. So they take the diffeomorphisms of a sphere and they promote it. So this is the unit disk bundle. This is the unit disk bundle. And strictly speaking, it should be the cotangent bundle. Okay. And I'll just say in words what to do here. The symplectic structure here is the standard symplectic structure. If you differentiate a diffeomorphism, it's by construction a symplectomorphism, but non-compactly supported of this manifold. And it's a bit like a Milnor trick. You have a compactly supported symplectomorphism here, which is the Dane twist. So you take your diffeomorphism. This is not a homomorphism, this is just a map. And you map it to the derivative of f in a bigger sigma inverse, df inverse. And this is a Dane twist. And it's, if you want to be precise, it's a half Dane twist. So on the 0 section, it's the antipodal map. That's still a perfectly good symplectomorphism. Now, unfortunately, I've messed up my diagram, but these symplectomorphisms in particular fix the 0 section. So you get you just get a restriction map, restrict to 0 section. And if D is even on homotopy, this map is morally multiplication by 2. So in very many cases, and in cases of interest, this map is multiplication by 2. If D is even. The point being, I see an inverse of F here, but the antipodal map, the Dane twist is the antipodal map on an even sphere that has degree -1. So these, if you compute these two mod out. So this is nice. We can put now, whenever you have a rationally non-trivial family, I should have improved the notation. This should be relative to the zero sphere. Set-wise, so a zero sphere. This is set-wise fixing the zero sphere, zero section. So if you have a family here that's rationally non-trivial, you get to multiply it by 2. It's still rationally non-trivial here. And we have lots of interesting topology now in symplectomorphisms, but set-wise fixing the Lagrangian. And one of the motivations for defining these kappa classes was trying to get an invariant that would allow us to remove the relative and make a statement about simp in general. But so far we haven't succeeded in doing that. So we have non-trivial rational families here of symplectomorphisms relative to a Lagrangian, but we don't know what happens if you remove that and pass to the full diffeomorphism group. So for people who like to study exact sequences of embedding spaces, right, in general, Diff of M set-wise relative to a submanifold. We saw this in Ryan's talk, for example. This is not really embeddings, right? Submanifolds, right? Knots A into M. If we could understand this homotopy sequence, that would be great. Just another comment. This group sits inside the symplectomorphism group of lots of symplectic manifolds, right? You just need a Lagrangian. Because it's relative to the boundary, you can put it into lots and lots of. So if you happen to find rational homotopy here, you have a good chance to try and put it into bigger manifolds. Okay, so there's work to do here. And I honestly don't know what happens when you remove the condition. I have no idea what to expect when you remove the condition of being setwise relative to the Lagrangian. So that's a little comment. I think this is a beautiful map. Evans and Rizal showed that it's non-trivial for finite homotopy groups, but this was a strategy for saying something for rational homotopy groups. Okay, that's it.
Questions? There's also non-trivial homotopy in odd dimensions.
Mm-hmm.
I guess theorem A works fine for that, but it's not on Blackboard anymore.
Well, yeah, I don't have a class. It's only if you have remember this cohomology class, the surreal Pontrjagin classes are special. They de-looped d times. Right, so even if you detect something that's non-trivial in homology of diff d, the Weiss families are special because the detecting cohomology class desuspends d times. Right? That statement makes sense, right? Because there's a default loop space going on here. So we're using the linearization version here. So, that would be great. But now if you have something in the cohomology, so there's a general strategy here. If you find something in the cohomology of a diffeomorphism group, a relative cohomology, but you would need to de-loop it to get the corresponding surreal characteristic class. So this is more a mechanism. If people find more interesting things here, okay, then there's then there's just a yoga, right? But you need to find the non-trivial characteristic class here to apply this relative kappa class yoga to it.
More questions? Well, if not, then we thank the speaker.
Last comment. Is it expected that the homotopy type of the symplectomorphism is different from the diffeomorphisms here?
Sorry?
Is it expected that the homotopy types are different?
Sure. I mean, you should ask Ivan Smith while you're here, or Oscar. Well, I don't know. But I guess people would be interested to show simp and diff are rationally different for a symplectic manifold. I don't know if that's been proven.
Actually, another question. Do you have an example where instead of this relative guy going to BDiff, it's hit from behind, from B-top?
No. I would love to have that. Well, maybe integrally. But But in the range, the only example I know of something rationally non-trivial here is again one of Michael's classes. So that's it's just really, the point is that we don't know much about this. We've got the first little bit of information here. If we're working rationally, of course integrally I think it's an interesting question. You could apply the techniques. We didn't think about that.
Okay, that was probably all. Any questions? More? Okay, let me